Yeah, hi, I'm in cast law 175 and I put the trying to use my laptop and it's not displaying on the screens. I don't think the screens are turning on. Yeah, Jay Parkinson. Okay. Both PCs are on, there's two screens in front of me, but nothing on the projector. Screens have come down. No lights yet. I've got one screen. It's a tablet connected with USB-C, and it does usually work. I've just used it the previous hour. No, it's a Apple. Yes, exactly. Yeah. Only one was lighting up earlier. Nothing's on now, but it was the one on the right hand side. And now both are on. Yeah, sure. Yeah. Okay, I just did that. I mean, my tablet recognises something's plugged in because the screen slightly changes. That's great. Okay. Okay. Thank you. Okay, see you soon. Bye. Okay, so as you probably realise, there's something wrong with the AB, so we'll just use the blackboard. Someone will come. It's probably just a little connector thing or something. Someone will probably fix it midway through the lecture. But for now, we'll go a bit old-fashioned. Use the blackboards. I'll turn the lights on. It's not unusual at the start of semester for some of these little converter plugs or whatever not to be working. So we probably won't get all the way through the lecture today, but when that kind of thing happens, often I'll use a tiny bit of the practice class on Thursday to just catch up anything we don't get through, okay? But otherwise, anyway, so we're on last time. And of course, there won't be a recording today. Well, there might just be the voice, but that's all. So we had a course introduction. And we looked at fields. And in particular, we looked at axioms, ZP, subfield criteria, some basic properties like the zero is unique and all that kind of stuff. Okay. Today, we still have a little bit to say about fields. And then we'll move on to vector spaces. And with vector spaces, we'll basically have some axioms, some examples, and basic properties today. But first, let's finish off what we were talking about with fields. So infinite versus finite. This is kind of an initial dichotomy that's kind of clear, that we have the reals, complexes, and then we have things like ZP. So there's lots of infinite fields. And we'll see some in a second. Here is an important class. So an important class that were called the algebraic number fields, and they're made in the following way. So these are all going to be subfields of the complex numbers. There are fields that are bigger than the complex numbers too. All kinds of things you can do, but this family we're going to make are fields that sit inside the complex numbers. So let alpha be a complex number, be a root of some polynomial. Let's call him P of x. So it's a polynomial with what kind of coefficients? But rational coefficients. Remember that notation was polynomials with coefficients in Q, rational coefficients. Now let Q adjoined alpha. This is this language we used yesterday. We had Q adjoined root 2 yesterday. Now Q adjoined any old root of a polynomial. And that's defined to be all of the things of the form A0 plus A1 alpha plus A2 alpha squared plus da-da-da-da-da plus AN alpha n, such that n is bigger than or equal to 0, and all of these coefficients are rationals. In other words, it's in fact the set of all f of alphas such that f is a polynomial with rational coefficients. Okay? So it's all of the all polynomials with rational coefficients evaluated at alpha. So the n can get bigger, of course, and so there can be big things, but finite sums. Everything's a finite sum. Now, it's a non-trivial fact that Q adjoined alpha is actually a field. Well, we could, with a little bit of time up our sleeves, we'd be able to sort of sketch how that proof goes, but it's best to just do it properly. Wait until Math 3962, where you'll see for a good reason why this is a field. That's the Galois theory course. And such a field is called an algebraic number field. And there is a super beautiful class of examples. As I've said before, something called algebraic number theory is just studying these fields, basically, like understanding their properties. All right, let's go through an example. So the point of this, introducing this example, is just so we're not stuck with our boring examples of Q, R, C, and ZP. I mean, we want a bit more to play with. This gives us a lot of stuff to play with. Okay. So an example, let's take alpha to be cube root of 2. So we'll beef it up from last time's square root of 2. We had a discussion about what Q adjoined this should be. It couldn't just be A plus B times this. You had to have this thing squared as well in there and so on. So notice that this is a root of P of x equals x cubed minus 2, of course. So it's of the right form. Okay? It's a root of some polynomial with rational coefficients. So in particular, alpha cubed is 2, of course. I mean, well, from the polynomial or just from the expression there. And that means that, for example, alpha to the power of 4 is just 2 alpha. Alpha to the power of 5 is 2 alpha squared. Alpha to the power of 6, and so on and so forth. That would be 4, and so on and so forth. Okay. So the point is, when I have such a combination like this, I'm only going to, once I can regroup everything into, it sort of cycles around. I get a rational number once I cube the thing. So I put that back in the A naught part, let's say. So I only get 3 terms in the sum. Q adjoined cube root of 2 is all of the things of the form A plus B cube root of 2 plus C cube root of 2 squared, such that A, B, C are in cube. So let's just quickly, maybe it's a bit, let's write it as A plus B alpha plus C alpha squared. It's a bit, just to, yeah. Any questions? Yep. And of course, how do you multiply things in this field? It's the obvious way, like expand everything out. It's a bit like, it's like using the complex numbers now. Complex numbers are an example of this, in fact. You take the polynomial x squared plus 1 here, introduce a new symbol, alpha being the imaginary unit I, and then the complex numbers would be q adjoined I. Sorry, not complex numbers, that's the sort of rational version of the complex numbers. You could do r adjoined I as well. Real numbers adjoined I, that's just the complex numbers. And when you multiply, it's the same kind of flavour. You take an A plus B alpha plus C alpha squared times an A prime plus B prime alpha plus C prime alpha squared. Expand it all out. Every time you see an alpha cubed, replace it by 2 and rewrite it back as something plus something times alpha plus something times alpha squared. Okay? Maybe more or less trivially, how would you find inverses? That's what you need to, that's the key thing about being a field, and that's the part why it's a non-trivial fact that everything in here has an inverse. That's the non-trivial part. But let's just do it in this example. Well, we'll just do an explicit example. Let lambda be 1 plus, so with this alpha up here, cube root of 2, plus 2 alpha squared. This should have an inverse. So let's take mu to be A plus B alpha plus C alpha squared is the inverse if lambda times mu equals 1, of course, which is 1 plus 0 alpha squared, if you like. Now, how we find that lambda, how we find that mu, we just do the product. We do it in a fairly by explicit calculation, really. We take our 1 plus alpha plus 2 alpha squared, multiply it by A plus B alpha plus C alpha squared, do the expansion as is obvious, and let me skip a little bit to what you get, dot, 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 dot. If you expand that out, you get A plus 4B, let me check I've done the same A's, B's and C's, yep, plus 2C plus A plus B plus 4C alpha plus 2A plus B plus C alpha squared by expanding out and using alpha cubed equals 1 as many times as we need to. But that's meant to equal 1 plus 0 alpha plus 0 alpha squared. So we get, in fact, 3 linear equations in the 3 unknowns A, B, C. And really, technically there, to equate the coefficients, we're actually using the fact that 1 alpha and alpha squared are linearly independent, which we'll sort of discuss a bit later today, in fact. But anyway, you equate the coefficients there. And there is something to say there. It's that alpha squared can't be written back as a linear combination of 1 and alpha. That's something I sort of asked you to prove last time, actually, to check that Q adjoined root 3 was not just that. And that's basically to show that alpha squared can't be written in that form. Which you have to do some stuff. So for this, we write out our matrix equation. Just to remind us, we write out an augmented matrix. It is a linear algebra course, after all. We row reduce it down. I haven't recorded what the answer was, an exercise, and eventually you get, so you're trying to find A, B and B, A, B and C, and you'll find as an exercise that A, B, C equals some things, 3 on 23. How you doing? Yeah, thanks a lot. Yeah. Yep, go for it, yeah. 7 on 23 and minus 1 on 23. So our inverse, lambda inverse, is that number in our field. Okay, so now, as you actually see, by just going through the working, it's not completely clear at all, why I'm always going to be able to solve this equation. I don't get a system that's that has no solutions. So somehow this coefficient matrix we're always going to get here has to be invertible, and that's a bit of the mystery of this statement here. Okay. But anyway, you're welcome to think of why it's a field, but as I say, I won't go into more details now. Any questions about that? Yeah?
Is there a reason that the elements of cube alpha is practice because the kind of alpha is always equal to the alpha?
Why they're always of that form? You mean always in this form here? Yeah, and so that's because they're always combinations of lots and lots of higher powers of alpha. But because alpha cubed equals 2, every time I see an alpha cubed, I shouldn't write alpha cubed. That goes back to this part. So if I have like 7 alpha cubed, that's actually equal to, because that's 2, that's 14 plus 0 alpha plus 0 alpha squared. So that would be its standard form, let's say.
So is n the degree of the polynomial you took out?
Good, except I could have also taken this as a root of x to the power of 6 minus 4. There's something called a minimal polynomial that has, so every number that's a root of some polynomial, we'll think about now factorising that polynomial over the rational numbers, where I'm only factorising using rational numbers in the factorisation. It'll be a root of one of those factors. There'll be a smallest factor in a certain sense in terms of degree. And one less than that power, the cubed here, is what I have to take here, the square. But since I start the indexing at 0, I'll get 3 terms. Yeah, exactly. So the degree of this minimal polynomial, which we will come back to something about minimal polynomials later on, in fact. But that's the idea. There's a bit of subtlety there about the existence of minimal polynomials and irreducibility of polynomials over the rationals. And it's really this irreducibility that this minimal polynomial doesn't split any further. That's what gives the fact that it's a field, in fact. But the way it really gets done is you look at the polynomial ring Q adjoined X, and you quotient it by what's called the ideal. It's like a subring kind of idea. The subring generated by that minimal polynomial. And then you prove that that quotient ring, so you have to have studied rings and quotients, that quotient ring is a field by showing actually that that ideal is a maximal ideal, the one that you quotiented out. So it has a very natural statement a bit later on. Yeah? Yeah, it's always for every number that is a root of some polynomial, there'll be a minimal polynomial. And that's the unique polynomial of smallest degree with, and to get the scaling right, make sure its leading coefficient is a 1 to just get, otherwise you can multiply by 17 or whatever. Yeah. But if you take some number that's not a root of any polynomial, then there's no minimal polynomial, like pi. I mean, it's not a root of anything. Good. It's a super fascinating area, and there's a lot more to say about algebraic number fields, but you can already start playing around with them like now. But let's look on the other hand, on the other side of this coin, there's the finite fields.
Looks like I've got it up.
Oh, good one, mate.
Do we test the projectors now? Or?
Yep, thanks.
Have you?
That's okay, no problems. We'll just check the projectors for a second.
Was it showing you before?
No, it wasn't, so that's a good sign.
Yeah, I think it's just waking up the signal chain. I just plugged my phone in and then...
Oh, good, okay.
Oh, now it's disappeared.
Oh.
Current input timing is not supported by the monitor display. So it's display settings on here. That must be in this app.
Oh, that's weird, because I just used it the last hour in a different room.
Yeah, each room is built differently. Might just have to look. So it's saying 920 to 1080, 60 hertz. Do you know how to get to the settings? What app is this that you're using?
It's just Notability, I think it's called.
If we go back, we'll just go to the main.
Oh, yeah. And then, do you mind if I unplug it? Just because it gets recorded otherwise. And then that.
Sorry, I don't know this app. I might just.
No, that's okay.
I might just look in
In there somewhere.
Yeah, look at
Could we lift up this screen and I'll continue? Okay, anyway, we'll continue. So on the other hand, compared to these algebraic number fields that are like, there's just billions of them, take any polynomial, like any polynomial, let alpha be a root of it, and you've got one of these fields. And they're sort of all different unless your root was a root of the same minimal polynomial. Like a minimal polynomial has a collection of roots. All of those roots are going to give you, in a certain sort of sense, the same algebraic number field. Not the same, but isomorphic. And all the other ones are going to be different. Like Q adjoined root 2 is not isomorphic to Q adjoined root 3. I mean, they're different fields. And that we can see that because Q adjoin root 3 has something in it that squares to 3. Q adjoin root 2 doesn't have anything in it that squares to 3. I mean, so they're different fields. Anyway, so it's quite, but Q adjoin root 2 and Q adjoin minus root 2, they're the same thing. Q adjoin cube root of 2. This is actually not the, Q adjoin cube root of 2, and you could add some omegas in there. That'll now have omega times cube root of 2. That'll be now something in the complex numbers, but it'll actually be isomorphic to Q adjoin this real number, cube root of 2. It's quite sort of interesting. It's because they're all linked by this minimal polynomial. Anyway, but on the other hand, finite fields are super rare. So there's a theorem from a while ago, 1893. Forgotten what his first name was. But, and that says the following. First of all, if F is a finite field, then the cardinality of F is P to some power n for some prime P. And n an integer. So first of all, the cardinality. So when you've got a finite field, you can talk about the number of elements in that field. That's heavily restricted. You can't have a field with 6 elements. But you could have one with 8 elements. That's 2 to the power of 3. Okay. And secondly, once you fix a P and an N, there's only one such field. And unique in this kind of context, as we discussed yesterday, is always up to isomorphism. I mean, you can rename what you're calling the elements, but unique means that any 2 examples with the same number of elements will have the same multiplication and addition tables. So up to isomorphism, field with p to the n elements. So again, that one is that's quite involved to prove. That's again a Galois theory. That's in 3962.
Sorry.
Oh no, that's okay. So that's showing that, but not the app. Yep. So once we've got that, we denote F with this bold F, P to the n equals the field with P to the n elements. And I'll write the in inverted commas like that. We've already seen that Fp, where the n is 1, Fp, by the theorem here, there's only one. We already saw that Zp is a field, so there it is. But if n is bigger than 1, then certainly Fp to the n is definitely not Zp to the n, because as we discussed last time, this guy down here is not a field, because p to the n is composite. Okay. The natural question is, how do you go about constructing these finite fields? And so when I post the PDF, there's an appendix that tells you how to do that. And it's sort of like the same thing we do here. We want to take a polynomial with entries in Z, with coefficients in Zp, okay, so polynomial over Zpx, and we sort of want to say that there's a root of it. So let's take a polynomial that doesn't have any roots. It's a bit more precise than that. I actually want one that doesn't factorize at all over Zp.
so that can't be factorised in any way. In particular, it won't have any roots, because if it had a root, I could factor out that linear factor. Okay, so it's more than just having no roots. It's saying that it doesn't, like you could have a degree 5 polynomial that factorises as a quadratic times a cubic. Okay, that's no good. I want just those, if that cubic couldn't factorise any further, that's the guy I want. Okay, so I've got a polynomial that doesn't factorise any further. And then there's a construction where we can sort of artificially build, in a certain sense, this root alpha to just be, in a way, it's a bit like with the complex numbers being introduced. You introduce a formal symbol, let's say, alpha, such that alpha satisfies your polynomial, such that p of alpha equals 0. So alpha's not in your original field, because we assumed that we didn't have any roots. But we add an extra element alpha that does satisfy that polynomial. So it satisfies some equation, a0 plus a1 alpha plus dot 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 plus a k alpha k, where k was the degree of our polynomial, equals 0. And then you take all combinations like this, just as we did, but the coefficients being in ZP. And then whatever the degree of that polynomial is, that's how many terms we're going to need here by this same business that happened, whatever, here with alpha. So now how many degrees of freedom, and then the remarkable fact is that this is a field. And I've sketched that in the appendix, how to prove that. And that'll also prove this case here, in fact, or same ideas. So remarkable that it ends up being a field. And we can count how many elements it has, because how many degrees of freedom do we have? We have k, or whatever the degree of the polynomial was. Let's call it n. N was the degree of the polynomial. We have n choices of these coefficients. Each of them come from ZP, which has p elements. So we've got p to the n. So that's our field with p to the n elements. So the recipe, at the end of the day, if I want a field with p to the n elements, I need to dream up a polynomial with coefficients in ZP of degree n, which doesn't factorise any further. Now, it's not clear that such a thing always exists, but it does. Okay? There's more than one of them, typically. There's lots of them, in fact. But and then you make this field in this way, all those fields are going to be isomorphic to one another. So you can do it in different ways, this field with Pn, p to the n elements, but the theorem tells us they're all the same, up to isomorphism. Anyway, so that's the recipe. Now you can do that, and it's quite informative, I think. How are we looking?
We're good.
Oh, good. Okay, what happened? Yeah, thanks.
Yeah, it's actually in the app, so that little display button.
Oh, right.
You click on that while you're in.
Is that all it was?
Then you select the screen
Oh, okay.
rather than presentation.
Oh, maybe I bumped it in the last lecture or something.
Every time you unplug
He might reset.
just reset the default.
Oh,
So
okay.
I don't really know, but yeah, that fixes it. So.
Oh, that's fantastic. Thank you very much. Yeah, I think let's go to iPad now. Thank you.
Use that one side and then use Blackboard on one side. And
I'll use both because I like freezing one. Yeah.
Oh, yeah, no worries.
Yeah. Okay, that's awesome. Thank you.
yeah, you're welcome.
Cheers. Okay, so let's, for the last 15 minutes, we'll just turn the lights down a bit. Any questions? I hope the point of this, so we can't, unfortunately we can't talk about fields forever because I'd like to, because they're really, really, really nice. But it's an advertisement really for next year where to really study fields properly, you have to slow down. You have to first talk about rings, ideals in rings, principal ideals, prime ideals, all this kind of there's a bit of general theory that then makes the development much smoother and more natural at the end of the day. But luckily we can see enough kind of cute examples. All these, get rid of that somehow. All of these, anyway, it's funny, it's quite small. Anyway, it's a different setting than what it previously was, but I'm happy. We can see it. Anyway, this is all what we talked about. I'll fill in the details. That was the cube root of 2 example. This was what we just talked about with finite fields. This was this, and we're up to vector spaces. As I say, we're not going to get all the way through vector spaces, but let's say something at least. And also, as you see, there's this big appendix at the end which talks about what I was just saying. Here it is here. All right, so let's get started with vector spaces and continue on Thursday, I think it is, our practice class. The motivating example in a vector space for vector spaces is Rn. That's our favourite one. That's where our vectors now normally think of as column vectors. So it's a book with n real numbers, and we add two vectors together just by adding them component-wise. We multiply a vector by a number by just popping the number into the vector. Of course, we could do that over any field. Take any field, take now a vector, a column vector, whose entries are all in the field, add two vectors just by doing it component-wise, multiply by something in the field by just popping it into the thing. That's the structure that a vector space has to have. We have to be able to add vectors together, and we're not asking to multiply vectors. That's too much structure for a vector space. We're just asking that there's some field, some underlying field there that we're allowed to do scalar multiplication. Multiply a vector by something in the field, the scalars. All right. And of course, it should satisfy all of these nice axioms that vector spaces should satisfy, and here they all are. It's again like the same with the axioms of a field. They're not remember them as VS1, VS2. I mean, this numbering is completely arbitrary again. It's remembering what the point of all of these axioms are. So a vector space starts life with a field. That's part of the definition. And we're not really defining just a vector space. We're defining a vector space for that field. So it's an F vector space. Okay? An F vector space is a set V. It's equipped with two operations. Again, by saying that there's two operations, I mean if you take two vectors, x and y, which for now I'm going to draw with squiggles under them. Sometimes I'll stop drawing squiggles, but for now it is a bit helpful to know what's a vector, what's a scalar. When I add two vectors together, I should get another vector. It's something in V again. And when I have a vector and a scalar, something in the field, this thing is again something in the vector space. That's the point. And the operations are meant to be they're not meant to be a shock. They're meant to be encouraging, in fact. When we add two things, it doesn't matter which way we do it. It should also be associative, the addition. There should also be a zero vector, which in this concrete example we were talking about, that's with all the zeros down the thing. So there's a zero. Here it's a bit important. There's a zero vector. That's not the number 0, but anyway, well, I haven't got the number 0 here anyway. But 0 in V, and that's its defining property. Well, there's at least one of them. We'll show in a second that it's unique. Every vector has an additive inverse. Okay. Again, it'll be unique, the additive inverse. We do need a few little compatibilities of how the scalar multiplication works. This one, in a certain sense, is like a normalization type of thing, that 1 times x equals 1, so that's the 1 in the field, times x equals x for all x. Now we need a few, these are, again, some kind of associativity rules. They're telling us how doing a product, that's a product of scalars times x, and that's a scalar multiplication followed by another scalar multiplication. But it doesn't matter which way you think about, they're the same thing. Okay? So they're all like subtle differences, of course, but the axiom is saying they're actually the same. And this is like a distributive law telling us how if I do an addition over the scalars, how does that manifest itself as something in the vectors, addition of vectors. I guess really formally there's sort of brackets around here and here, but it's that implied notation that multiplications are done before additions. I mean, sort of there's an implied bracket around those guys. Similarly here. Okay, that's another distributive. So sort of two distributive laws, subtly different. Anyway, as I say, it's not meant to be a shock. It's meant to be nice. Now, if the F in our vector space is clear from the context, that we're just, we're in a certain part of the lecture or a problem or whatever, a question, we're always working over the same field, we might just call something a vector space without insisting on F vector space. As I say, typically it is nice at the beginning to use squiggles under something. to highlight that they're vectors, just to distinguish them from scalars. Here's lots of examples. If F is a field, this is just the natural generalization of Rn, where we replace R by any old field. So that we look at column vectors. I'll usually use square brackets for vectors. You can use round ones, whatever. But square brackets for matrices. And all of the components are in F. This is an F vector space where we do everything in the natural way. Here's the definition of the two operations. You could check a few axioms, if you like, as an exercise. Okay. However, again, it's meant to be completely clear. Another one is this ring of polynomials with coefficients in F. Well, yes, it is a ring, but actually it's also an F vector space. That's a lesser structure, right? Like when I talk about this set of polynomials and call it a ring, that's where I'm including in my mind that I'm allowed to multiply two polynomials, or I have that structure in my mind. But if I say this thing is a vector space, I'm sort of, it's somehow contextually that I'm not thinking about multiplying polynomials, because that's not part of a vector space. All I'm thinking of doing is adding polynomials and multiplying polynomials by a field element, by a scalar. It's fine. It is also a ring, but that's got extra structure. So that's certainly a F vector space. And this one here, this notation we'll use, so take note of this, where I put the little n down the bottom. That means all polynomials with coefficients in F of degree less than or equal to n. That guy is also a vector space. However, that one's not a ring, because if I multiply two polynomials of degree 7, I'll get one of degree 14. I mean, it won't be closed under multiplication. So maybe I'll just say that. And I'm just really saying, so it is not a ring. I'm just saying that to highlight. There's a structure, to think of what structure certain things have, like what's a ring, what's a vector space, what's a field, and so on and so forth. The next one is another way of making a big vector space from, this guy's not a ring unless m equals n, because I can't multiply matrices together. So now this one's left the ring world. This I can certainly add to m by n matrices together, and I can certainly multiply them by a scalar. And with those natural operations, it's an F vector space. We haven't talked about dimension yet, but what would the dimension of this vector space be already, if you're just starting to think about it? Yeah, m times n. And a basis would be the matrices with a 1 in one entry and zeros everywhere else. Those guys, everything can be written as a linear combination of those, and they're clearly linearly independent, in fact. They're things we're going to refresh in a bit later on, early next week. But anyway, this would be and this guy here would be a bit of a trick with where the indexing starts. This is an n plus 1 dimensional vector space, because you've got the constant terms. This guy up here would be an infinite dimensional vector space. Anyway, we'll come back to that more concretely. Here's a few other ones. We'll just define a heap of vector spaces, and we'll really use these examples in our examples and explanations and stuff. So here's one just called sequences over F. So again, F is always a field. This is going to be all sequences with entries in F. So this does go on forever. That's fine. It's not when I'm talking about convergence sequences or anything like that. It's just an infinite string of elements from F. I add them together in the natural way. And I do scalar multiplication in the natural way. Again, you should just check a few axioms to check that, or just look at the axioms and convince yourself this is obviously a vector space. Again, infinite dimensional, because we could take infinitely many linearly independent things, the sequence with a 1 and zeros everywhere else, then a 1 and zeros everywhere else, and so on and so forth. more and more examples. There's lots of vector spaces. Now we can take functions from a set, X is just any old set, into F, our field. This guy is an F vector space. Less obvious what's going on here, but you do. I think it's worthwhile actually looking at some axioms for yourself. I'm not going to do it here, but the sum of two functions, f plus g, is the function whose value at x is f of x plus g of x. Notice that I need the outputs to be in an f so that I can actually do this addition. This is the addition in f here in the underlying field. And the scalar multiplication is just, well, this is lambda f of x. No, bit of a no-brainer, that one. But anyway, but the point is check some axioms, that that's really a vector space. Another example, I think I've got just a few minutes. We might get I might almost get it said today. Well, I won't rush, we might come back to it. But so this one is a good, an important example. So now if we've got two fields with one a subfield of the other, so F a subfield of E, okay, so remember what that means, then I can regard E as an F vector space. It's kind of an important thing, in fact, this idea. And the point is, the vector addition, so, okay, so we have to separate, so we've got E as a big field, for example, the complex numbers, and F as a smaller field, like the real numbers sitting inside it. Okay? And now the vectors are the complex numbers, and I add them just using the field addition in the complex numbers. And scalar multiplication, well, that's actually just restriction of the field multiplication in E. But I'm just insisting the first guy is something from the smaller field, the reals in this case. So this is just a real number times a complex number, which is a sub case of complex number times complex number. Then these are, so that they're just restrictions of the normal operations in E, or this also, just going through the axioms immediately, this is a vector space. I mean, without, just basically the field axioms guarantee that this is a vector space. So for example, R is a Q vector space, C is an R vector space, and R is any subfield of R. For example, Q adjoin root 2. It's a Q adjoin root 2 vector space. And you can start thinking about the dimensions of these. This one's easy. C as an R vector space has what dimension? 2, A plus IB. The Cartesian form of a complex number is writing it as a linear combination of the basis vectors 1, I. This guy is harder to see, but already like a countability, uncountable argument says this is infinite dimensional. So there's not a finite set of rational numbers such that every real number can be, there's not a finite set of real numbers such that every real number can be written as a rational combination of that finite set of real numbers. Okay, so that one's infinite dimensional. This one also infinite dimensional. But anyway. And just one more example just to add on to there. Something like Q adjoin cube root of 2 is a Q vector space. So this one is infinite dimension. This one is 2 dimension. This one is infinite dimension. And this one is 3 dimensional. We'll come, the lemma's just going to say, just to flash it up, it's just going to say all these nice properties about are all true, like, for example, the number 0 times the field element 0 times any vector is the 0 vector, so on and so forth. Let's come back to that in the practice class on Thursday. Any quick questions? All right, practice class, we'll spend 10 minutes, something like that, finishing the lecture, and then move into the practice class. Good.
Just a quick question about notation.
You know how, for example, when we're defining the array number field, you know how you use sometimes like Q of square brackets x as opposed to round number of n something?
Yeah, Q of square brackets are polynomials.
Okay, so is that this convention?
And then the round brackets is this adjoining stuff. Yeah, that's right. So it's a bit different. I mean, that notation does also come from somewhere. The square brackets is a ring extension, and the round brackets is a field extension. It's the way it happens later on. But anyway, for what we were talking about, the square brackets exclusively use polynomials, coefficients, and whatever, Q or whatever.
So with the square brackets, would that still be restricted to, is those x's still restricted to like the values that we can take? Like, you know how...
The x's here is like a new object.
So they're not under the same
symbol.
restrictions.
That's right. The alpha, when I do Q adjoint alpha, that alpha is some number that's a root of some polynomial.
Yes.
But the Q square brackets x, that x doesn't satisfy any relation. I mean, in a way, you should think of x as some new variable that doesn't satisfy any polynomial equation.
Okay.
So actually, you can take it to be concrete. You could take it as pi. Q round brackets pi actually is the same as Q square brackets x, where x and pi just get matched up, because any polynomial in pi with rational coefficients, that can't be simplified. That's the point, because pi doesn't satisfy it.
All right, thank you very much.
Can I ask you a question about the exercise you did last week? Because I thought about that a lot. So we're supposed to show that something like a plus root 2qb, where a and b are rational numbers, it's not a field, and the integral that is there. It's like plus under multiplication, right? So if you suppose that the 2q as a plus
Square, I guess.
yeah, so 2 over there is equal to a plus 2 over b.
Yep.
Then if you multiply this by 2 over 1/3, you get 2 equal to 3 half 1 a
Yep.
plus 2 half 1/3. And if you use this one,
Perfect. Use it again. Yep.
you get 2 equal to, I think, if you click everything, you end up with 8 plus
So like in this case, that's what you're saying. Like you can kind of do that.
plus 8 plus 2 squared.
Good.
Yeah.
I mean,
It's not the same as your
Yeah, good.
inverted.
so on the left hand side you have a rational number, but on the right hand side, well, this is a rational number, this is a rational number, this is irrational. So the only way that this can make sense is for this thing to be 0.
Perfect. Yep. Perfect.
Right? So then if a equal to minus b squared, then ab is actually minus b cubed.
Yep.
So minus b cubed is root 2q. Sorry, is 2.
Yep.
So b is just
Good.
minus.
A contradiction because that guy's irrational. Yep. That's perfect. Perfect. That's good.
I was thinking about minimal polynomials, like if you can like x cubed minus 2. But then that cannot, you cannot actually reduce this further in rational numbers.
No, exactly. You can't. Yeah, and there's various there's tests that to see that you can't do that. I mean, generally it's a hard problem. You have a big polynomial, degree 50 or something, to know it can't factorize as a degree 40 times a degree 10. It's a hard question, but there are algorithms to do that. And there's quick tests. For example, this is an example of something called Eisenstein's criteria, that you can straight away see that is we might talk outside in case there's another class, but I do want to clear the board. I should do that. So I'll just quickly do that and then meet you outside.